Hi and welcome to this third video about the best methods to convert alkenes into epoxides. This presentation is about the epoxidation of electron-deficient alkenes, such as enones, acrylates, acrylonitriles, and related compounds. The mechanism of most of these reactions is a Michael-type addition of the oxidant to the alkene, followed by epoxide formation through an intramolecular nucleophilic substitution at oxygen. Suitable oxidants include hydrogen peroxide combined with a base, hypochlorite, peroxy acids, and alkyl hydroperoxides. Because this mechanism is different than that of the epoxidation of electron-rich alkenes, dienes with one electron-deficient and one electron-rich alkene can often be epoxidized selectively. Treatment of carvone with hydrogen peroxide and sodium hydroxide, for example, cleanly yields the epoxidized enone, as shown here. With MCPBA, however, the more electron-rich isopropenyl group is oxidized selectively. Also weaker bases, for instance sodium carbonate, may be sufficient to bring about the epoxidation of electron-deficient alkenes. Here, an enal was epoxidized selectively, without any oxidation of the formyl group. The rate of epoxidations of electron-rich alkenes correlates with their ionization potential, and not so much with steric accessibility. But enone epoxidations start with a Michael-type addition, and these are highly sensitive to steric shielding. Here, for instance, despite the excess of oxidant, the less substituted, sterically more accessible enone was epoxidized first and with high selectivity. Commercial aqueous solutions of sodium hypochlorite are strongly alkaline and can be used directly to epoxidize electron-deficient alkenes, as in this example. These solutions can, however, also chlorinate ketones, electron-rich alkenes, and arenes, and reactions as the one shown here may require some optimization. Occasionally, such epoxidations have also been performed with the aid of acidic catalysts. In this example, an enone was epoxidized enantioselectively with hydrogen peroxide and 5% of a chiral Lewis acid. Thioethers are readily oxidized to sulfoxides or sulfones by a number of oxidants. Nevertheless, it is sometimes possible to epoxidize alkenes without simultaneous oxidation of thioethers, as in this example. Usually also the thioether will be oxidized, however. This here is another rare example of epoxidation of a thioether, again with hydrogen peroxide as oxidant. The oxidation of thioethers by hydrogen peroxide usually requires catalysis by acids, and is apparently sufficiently slow to enable clean epoxidation of enones. Also amines can be oxidized by hydrogen peroxide. In this example, however, the epoxidation proceeded sufficiently fast and no significant amounts of amine oxide were formed. Also unprotected anilines may occasionally remain unchanged during the epoxidation of enones. Here an excess of hypochlorite was the oxidant, and surprisingly no chlorination of the carbazole substructure occurred. Enones can be epoxidized enantioselectively with alkaline hydrogen peroxide and polyleucine, as shown here. Again, an aniline substructure did not require any protection. Deactivation by the keto group probably helped here to prevent aniline oxidation. In this example, an enal was epoxidized by treatment with alkaline hydrogen peroxide. Neither the aldehyde nor the hydrazine were oxidized, but stereoselectivity was poor. Phenols, in particular catechols and hydroquinones, can also be readily oxidized. Dimethyl dioxyrane is particularly selective and well suited for the epoxidation of enones containing phenol substructures. Here, a hydroquinone could be epoxidized in fair yield with an excess of dimethyl dioxyrane. The hydroquinone of the previous example was not very sensitive toward oxidants, but enones like the one shown here could not be epoxidized in high yield with any other reagent than dimethyl dioxyrane. Both alkaline or acidic reagents caused nucleophilic attack by the hydroxy group at the epoxide and its ring opening. With dimethyldioxyrane, however, a quantitative yield of epoxide resulted. Like thioethers, also sulfoxides can be oxidized to sulfones. In this example, it was possible to epoxidize an alkenyl sulfoxide in moderate yield and diastereoselectivity with anhydrous terzbutyl hydroperoxide and potassium hydride as base. With a larger excess of oxidant and base and a longer reaction time, 10% of a sulfone was obtained. A number of strategies exist for the enantioselective epoxidation of electron-deficient alkenes. One of them is the combination of a chiral quaternary ammonium salt with a hydrophilic oxidant in a biphasic reaction mixture. Quinine derivatives seem to work particularly well, as shown here. In this example, a nitroethylene could be epoxidized in high yield and with good enantioselectivity with a sodium hypochlorite and 10% of a quaternized quinine derivative. Still higher enantioselectivity could be attained in this example, with hydrogen peroxide as oxidant. Concentrated aqueous potassium hydroxide should not be mixed with chloroform, but no larger amounts of carbene-derived byproducts were formed here. Also, the thiophene remained unchanged, despite the large excess of hydrogen peroxide. Proline derivatives can also be used as catalysts for enantioselective epoxidations of enones. These reactions probably proceed by intermediate formation of an iminium salt, which then reacts with the hydroperoxide. Cationic iminium salts are more electrophilic than ketones or aldehydes, and the high enantioselectivity suggests a covalent adduct of catalyst and starting enone. Ketones, as the one in this example, do not react quickly with amines, though, and the epoxidation took a long time. Alpha-beta unsaturated aldehydes are better substrates for pyridine-catalyzed enantioselective epoxidations, because aldehydes are more electrophilic than ketones and react faster with amines. Here, 10% of catalyst were enough for a full conversion of the starting enal in only 2 hours at room temperature. So, what can go wrong? Bases can induce aldol condensation of ketones and aldehydes, in particular at high concentration. This and the decomposition of reactive epoxides by rearrangement or nucleophilic ring opening are two important potential side reactions. Then, some starting alkenes with particularly reactive allylic CH groups may undergo allylic oxidation, as in this example. Transition metal catalysis can worsen this problem. Here, a manganese complex caused extensive allylic oxidation already at -40°C. The peroxides formed in the first step of the epoxidation of electron-deficient alkenes are stable under neutral or slightly acidic conditions, but can be converted into epoxides by treatment with a base. If acidic reaction conditions are used, such peroxides can therefore sometimes be isolated, as in the example shown here. With hydrogen peroxide under acidic conditions, enones are often transformed into cyclic peroxides, as in this example. One additional byproduct formed here was an isomerized alkene, which in this case was less electron deficient and thus less prone to epoxidation than the starting material. This is another example of the isomerization of an electron-deficient alkene into a less reactive one. Here, a large excess of a strong base was used, but, as shown on the previous slide, even weak bases can cause such deconjugations. Ketones and aldehydes may also undergo Baeyer-Villiger oxidation, even under basic reaction conditions. In the first equation on this slide, both epoxidation and Baeyer-Villiger oxidation occurred upon treatment of the starting enone with a large excess of alkaline hydrogen peroxide at 0°C. By diminishing the excess of oxidant and by lowering the reaction temperature further, the Baeyer-Villiger oxidation could be suppressed completely. Dioxyranes and peroxy acids tend to hydroxylate tertiary CH groups. In this example, treatment of a dienone with 3 equivalents of dimethyldioxyrane gave 4% of a tertiary alcohol as byproduct. Here are some more examples, but many more have been reported. You can also find these references in the description of this video. If you haven't done so yet, you may also watch the first and second video of this playlist, where the epoxidation of simple alkenes and of allylic alcohols and related compounds is discussed. There you can also find a more thorough discussion of potential side reactions.